In today's lesson, we're going to learn a more complicated phase diagram, the iron-iron carbide phase diagram. So on that phase diagram, we have iron carbide, which is an intermetallic compound. So let's take a look at the definition of intermetallic compounds first. So that's a compound formed from two or more metals, which has its own unique composition, structure, and properties. So those compounds are usually hard and brittle, so they're commonly used as dispersed phases to strengthen the material. So in those intermetallic compounds, we have stoichiometric interatomic compounds, which have fixed composition. And the other type is non-stoichiometric interatomic compounds. They usually have a range of compositions. So those compounds are typically used in structural, aerospace, and microelectronic applications. What you see here is the iron-iron carbide phase diagram, which is part of the iron-carbon phase diagram, because if you look at the composition axis, which is the weight percentage of carbon, is not from 0 to 100, but it's from 0 to only 6.7 weight percent of carbon. That is the composition of this intermetallic compound iron carbide. So it has a vertical line here on the phase diagram, not an arrow, because it is a stoichiometric interatomic compounds. It has a fixed composition. Next, let's take a look at three phase reactions in binary phase diagram, which we'll see in the phase diagram, iron carbide phase diagram in a second. So the first very important reaction is from one liquid phase transformed into two solid phase, and this is called the eutectic reaction. And the second one we will have very similar to the top one, but instead of transforming from a liquid, now we'll have a gamma phase, which is the solid phase. So from one solid and become two solids. This is called the eutectoid phase diagram or reaction, eutectoid reaction. And the last one, we will have alpha plus liquid. So alpha is here and the liquid phase is here. And the transformation or the reaction start from alpha phase, which is the solid, and plus a liquid, and it forms one single solid phase. So this reaction is called the peritectic reaction. Now let's take a look at the iron carbide phase diagram and identify those important reactions. Even without knowing the alloys on the phase diagram, based on the convention of naming the solid phases, which means solid phases are named as alpha, beta, and gamma, right? So we will know that this gamma phase and alpha phase, right, are solid phases, and then there's a delta phase as well, and we have these interatomic compounds is the solid as well, and L, you have the liquid here, right? And another way to identify reaction is your reaction will take place at a constant temperature, so you'll see those horizontal lines, those are called isothermal lines or isotherms, which means it has a constant temperature. So those lines all representing our reaction. Now let's see, where is the eutectic reaction? Eutectic is from one liquid to two solids, right? So this is the liquid and gamma phase is the solid, and the other side of the liquid, we have this interatomic compound, the iron carbide. So looks like this is the eutectic reaction. That's the isothermal line, and it happens at 1143 degrees Celsius. And the eutectic compounds is 4.3% of carbon right here, from liquid to gamma and iron carbide. The second reaction on this phase diagram would be the eutectoid reaction, and eutectoid is from one solid to two solids. So on this phase diagram, we have a solid here and solid at the far left here, very tiny region, and alpha as well is a very tiny region here, alpha, so that's solid. And don't forget we have this solid interatomic compound here. So based on that, right, the one solid to two solids, I see here at 727 degrees Celsius, there is one reaction, right? We have a gamma phase formed into two solid phases, the alpha plus the iron carbide. The eutectoid reaction happens at 727 degrees Celsius, and the eutectoid point eutectic composition is 0.77 with percentage of carbon, and this interatomic compound, the iron carbide, is also called cementite sometimes, or on some references. The last reaction is the peritectic reaction, where you have one solid and one liquid first, then it transforms to a second solid phase. So on the iron carbide phase diagram is over here on top portion at about 1493 degrees Celsius, very small region. And on top we have delta ferrite or delta phase plus the liquid, so one solid, one liquid, and it becomes another solid. So that solid is on the bottom region, which is the austenite or the gamma phase. So here's the reaction. Delta plus liquid at about 1493 degrees Celsius, and that composition point is about 16% of carbon. That composition is right here. Now let's look at the single phase regions or solid solution regions. So on the phase diagram, you can see here, there's a tiny region here labeled as delta, and below it, there is one single solid phase that's called gamma, and lower down, there's another single solid solution phase, which is labeled as alpha. Iron goes through two allotropic transformations during heating or cooling. So on cooling, so first we have liquid, right? It then transforms to BCC structure called delta ferrite. So this delta ferrite actually has BCC structure over here, and then into the FCC structure, which is austenite, or this gamma phase is also referred to as austenite. It has FCC structure. On further cooling, it reverts to the BCC structure again. This BCC structure is labeled as alpha ferrite or just ferrite. Ferrite or alpha ferrite is at this small region on the bottom of this phase diagram. It's a interstitial solid solution of a small amount of carbon dissolved in the alpha phase. So the crystal structure is BCC for alpha or ferrite, and the maximum solubility of carbon, that's the maximum solubility of carbon in alpha phase, is 0.0218%. That happens at 727 degrees Celsius, and at room temperature down here on the bottom, there's only 0.008% of carbon, almost zero at room temperature. And another important fact is the ferrite or alpha ferrite. It is the softest structure that appears in this phase diagram. Next solid solution is the delta solid solution or delta ferrite over here. Delta ferrite is an interstitial solid solution of a small amount of carbon dissolved in the delta iron, and the crystal structure is BCC structure, just like the alpha ferrite, and the maximum solubility is in this point, the max solubility of carbon in delta is 0.09%, then the stability of this phase is only in the range, over this range, temperature range, 1394, that's the temperature over here, and 1539, that's the temperature over here. That's the stability range of this phase diagram. So that means it's not stable at room temperature in plain carbon steels. However, we can do a special treatment so it can be present at room temperature in alloy steels, especially duplex stainless steels. The austenite located on the phase diagram in this region. Austenite is an interstitial solid solution of a small amount of carbon dissolved in the gamma ion, and it forms an FCC structure. So remember, we have BCC as the delta, and then transforms to FCC in austenite, and then back to BCC again for the ferrite. Right? So the maximum solubility is at this point, 2.11 at 1147 degrees Celsius. That means at that temperature, right, we can dissolve a maximum amount of carbon into the gamma ion without forming a second phase. And austenite has a hardness of 40 HRC and the toughness is high. The cementite on this phase diagram is located over here. Cementite or iron carbide, the chemical formula is Fe3C and contains 6.67% of carbon. The composition is labeled over here, and also that's a vertical line, right? If you still remember the composition of this interatomic compound. So it's hard and brittle interstitial compound. Actually, it is the hardest structure that appears on this iron carbon diagram. So, that being said, we said ferrite, right? Ferrite is the softest structure, and this iron carbide is the hardest structure. So we want to have a good combination of those two to have the best property of the material, or to achieve the property we want to have. Two very important reactions and points on this phase diagram are the eutectic point, where is the point A, and to write this eutectic reaction, again, you look for this horizontal isotherm or isothermal line, and we look on top of it, which is liquid, and we look at the two ends of it. So we have this austenite and we have cementite on the other side. So that's the reaction, eutectic reaction. And the eutectic composition is a composition of this point A is 4.3% of carbon. We looked at this eutectic reaction last class, right? We know we will have layers of structures or lamellar structures resulted from this eutectic reaction. So the next important reaction, which will be the focus of this class, is the eutectoid point, the point B here on our phase diagram. So the same thing, we look for this isotherm, the horizontal line, and on top of this line we have one face is a solid austenite, and on two ends of this line, right, this line ends at alpha phase, and on the right side ends on the cementite. So the reaction will be the austenite transformed into two solid phase. So this is the eutectoid reaction. And for the microstructure or microconstituent, first at this point, right, where we have one phase, just the gamma phase, we have a gamma grains only in this crystal structure. And as we cool down, there will be the eutectoid reaction, where from the gamma phase, the alpha and cementite will precipitate out into those layers. Okay, so we'll have alpha phase, which is this blue region in this phase diagram, and the cementite, which are the needle-like, but they also form the alternating layers. So just like your eutectic microstructure, they have layer structures, and we have a name for it. It's called the pearlite. Pearlite are alternating layers of soft alpha phase and hard brittle cementite phase. Pearlite, the alternate layer of alpha phase and cementite. So is the eutectoid mixture containing 0.76% of carbon, and it is found at 723 degrees Celsius on very low cooling. So it's a liquid equilibrium structure, and it is lamella mixture of ferrite and cementite. The primary microconstituent from the eutectoid reaction, we follow the same notation, or we form the same convention for naming those microconstituents. So divided by this eutectoid composition point, which is 0.76% of carbon, right? From the left end to the eutectoid point, we have hypoeutectoid steels. And then from the eutectoid point to the right of the eutectoid reaction line, we have hypereutectoid steel. For the hypoeutectoid steel, it's to the left of this eutectoid composition. Right, we cool from the austenite region. We have all austen first, and then we start to enter the austenite plus ferrite region. So ferrite start to precipitate out from the austenite. So this orange region representing the pro-eutectoid ferrite alpha phase. And when we reach the eutectoid temperature, the remaining austenite structure, so here's the austenite, will all transform into the pearlite. So that means in the hypoeutectoid steel, ferrite is the primary microconstituent, and then we have the pearlite with ferrite. On the other side, we have hypereutectoid. Again, initially we just have austenite, all solid austenite, and pass through the liquidus line or the solvent line, we will have the two-phase region where the cementite will precipitate out from the solid austenite phase. So that smaller orange region is the cementite. And at the eutectoid temperature, the eutectoid reaction takes place, then all the austenites will transform or react into the pearlite. So that means for hypereutectoid, it is cementite plus pearlite. So although below the eutectoid temperature, we only have two phases, right? We have the alpha phase and we have the cementite phase, but the macroconstituents can be different, right? On both sides of this eutectoid composition, we can have alpha, pro-eutectoid alpha, plus the layered structure pearlite, or we can have the cementite, the pro-eutectoid cementite, plus the layered pearlite. Here is the evolution of the hypoeutectoid steel microstructure. First, we'll have austenite, and the alpha phase start to precipitate out from the austenite grain boundaries. And alpha phase grows bigger. After the eutectoid reaction, all the gamma phases here will transform or react into the pearlite, become pearlite structures. So at the result, we will have alpha phase, which is the pro-eutectoid alpha phase plus layers of pearlite structures. Okay, it's time to do some calculations. Calculate the phase amount or the amount of each microconstituent. Here we're going to focus on the hypoeutectoid steel, where we have the original composition between 0.0218 and then the 0.76, the eutectoid point, right? Right before. Let's calculate the phase amount right before the eutectoid reaction. It's just right above the eutectoid reaction. So we're going to draw the tie line right at this region. Just before it, we draw the tie line, and on both ends of the tie line are the phases exist now, right? So we will have the alpha ferrite, and then we have the other side of the region. We aimed at the austenite region. So the two phases are alpha ferrite and austenite. So the amount of each phase, we will use the the lever rule again. Draw the tie line, and the length of the opposite length, the tie line S, right? For the phase amount, weight percentage of alpha phase will be the S over the entire length of the tie line, and the rest will be the weight percentage of austenite. So next, when we pass through that eutectoid reaction temperature, after, right below this eutectoid reaction, we will see a microconstituent, right? The microconstituent includes the pro-eutectoid ferrite, which is the blue region, and we have the layered microconstituent, which is called pearlite. But if you compare this microstructure on top and microstructure below, we can see, right, the pro-eutectoid ferrite doesn't change at all, and the pearlite is just all the austenite was replaced by pearlite. So that means the weight percentage of pearlite now is the same as the weight percentage of the austenite we calculated above here. Okay, and now those two are for the phase amounts. So we have alpha phase, we have the cementite, right? And again, we're going to use simply apply this lever rule. So the weight percentage of the overall alpha phase will be the S now, the capital S, this whole length here, over the entire length, alpha R plus S, and the rest will be the cementite phase. For the hypereutectoid steel, the evolution of microstructures are very similar, but slightly different. So first we have austenite grains only. Then the cementite grains or cementite start to precipitate at the grain boundaries of the austenite grains. And right before the eutectoid reaction, you can see the cementite grows bigger, and then we have the pro-eutectoid austenite. After the eutectoid reaction, all the pro-eutectoid austenite becomes the layered structures, which is the pearlite. So as a result, we have pearlite and the pro-eutectoid cementite. One thing I want to mention is the reason for the hypereutectoid steel is higher than the eutectoid composition, but lower than the composition of the eutectic reaction. So which means it's just between those two. It's not all the way to the right, to the 6.7 weight percentage. Okay, and another note is this point, 2.1% of carbon, that's the dividing point between steel and cast iron. So when the carbon content is below 2.1, that's a steel. But when the carbon content is above 2.1, it becomes cast iron. The phase amounts and microconstituents amounts of the hypereutectoid steel before the eutectoid reaction, we draw the timeline and we see we only have austenite and cementite. And the phase amounts, we can just calculate using the timeline, using the lever rule, the opposite lever tie line over the entire length of the tie line, and that is the weight percentage of austenite, x over v plus x, and the rest of it will be the cementite. And after the eutectoid reaction, all the pro-eutectoid austenite, this light blue region, transforms into the pearlite. So, which means the microconstituent pearlite has exactly the same weight percentage as the austenite we calculated earlier. So that's the value we calculated earlier, right, is the same as the weight percentage of the pearlite. And the weight percentage of each phase after the eutectoid reaction, again, simply apply the lever rule, draw the timeline. Now the timeline is longer than earlier, right? This is the V, the left side, and then X, the right side. So the weight percentage of the overall alpha phase, which includes the alpha formed earlier. Sorry, we don't have any alpha formed earlier in this case. It's just alpha formed at the eutectoid reaction. Here is x over the entire tie line, the length here, and the rest will be the ferrite. And ferrite now includes two portions. The first one is the pro-eutectoid ferrite, and then the second one is the layered structure within the pearlite structure. Let's take a look at one example here. So we're given the overall composition is 0.4% of carbon steel at a temperature just below the eutectoid. So based on this composition, it should be a hypo, right? It's below 0.76, which will be a hypoeutectoid alloy. So we're going to determine the compositions of the cementite, the iron carbide, and ferrite. And we're going to determine the amount of cementite that forms 100 grams of steel. So actually that's another way to ask the weight percentage of cementite, right? If we know the weight percentage, then we multiply it by the overall weight, we can have the amount, right? The weight of cementite that requires. And then lastly, we're going to calculate the amount of pearlite and the pro-eutectoid ferrite. So that means those are the microconstituents, right? We're going to calculate the amounts of each microconstituent. First, find the compositions of cementite and ferrite. We just need to draw a tie line, right? So the temperature we're looking at is right below the eutectoid reaction. So we're going to draw a tie line right below the eutectoid reaction temperature, right below there. And I'm going to read the compositions of the composition axles. So the C alpha, the composition of alpha phase is about 0, actually very close to 0, but it's about 0.022 weight percent of carbon. And the weight percentage or the phase composition of ferrite, actually, if we don't have to read from it because we know it has a fixed composition of 6.7 weight percentage of carbon. But again, it's given on this phase diagram over here, so which is the value. Next, calculate the amount of cementite in grams that forms in 100 grams of steel. Actually, you just need to find the weight percentage of cementite, right? And then multiply that by 100. That will be the weight. So since we're calculating the weight, the phase amount, so simply using this tie line, apply the lever rule, right? We are looking for the weight percentage of cementite. So just use the opposite length here divided by the overall length, which is R plus S. So use those compositions we figured out earlier, and C0 is given as 0.4, and calculate the weight percentage of cementite, or that phase amount. So is about 5.7%, which means, right, in 100 gram of steel, we have 5.7 gram of cementite. Last, we calculate the amount of pearlite and pro-eutectoid ferrite, which means we're calculating the microconstituent amounts. So if we realize that the microconstituent, right, pro-eutectoid alpha is the alpha phase formed before the eutectoid reaction, right before the eutectoid reaction, and the amount of pearlite is just the amount of the austenite right before the eutectoid reaction. Because during the eutectoid reaction, all of the austenite will transform into pearlite, and all the pro-eutectoid ferrite doesn't change at all. So that will make our calculation much easier, which means we just need to calculate right before the eutectoid reaction. So before the eutectoid reaction, we draw this tie line, and the C0 is still the 0.4 given value, and on that tie line, before the C alpha is 0.022, is the left end of the eutectoid line, which is actually 0.218. Okay, and this the eutectoid composition, which will be 0.76 with percentage of carbon. So that's the C of gamma phase. Again, all the gamma phase will transform to pearlite during the eutectoid reaction. So then we can calculate the weight percentage of austenite or gamma, and it is also the weight percentage of the pearlite. So use the lever rule, V over V plus X, and X is all the way extend to the right end of this phase diagram. And we calculate the weight percentage of pearlite is 51.2%. And the rest of it will be the pro-eutectoid alpha phase or pro-eutectoid ferrite. So the amount of pearlite, right, we just use 100 gram times the percentage, and it's 51.2 grams of pearlite, and that means we will have about 48.8 grams of pro-eutectic ferrite.